Here we consider one-dimensional kinematics, in particular the special case of constant velocity motion and constant acceleration motion, or motion with constant velocity. We've already talked about what position, velocity, and acceleration mean. Those are the kinematic quantities. And we've also talked about how they're related in one dimension in their position versus time graphs, velocity versus time graphs, and acceleration versus time graphs. But now we'll take this special case because it's a useful one that appears in a lot of situations that you might observe. So what we'll do is we'll look at problems where in some interval of time you can say, well, the object is moving with constant velocity during this period, and maybe in another interval of time the object moves with constant acceleration. And we'll actually continue this for another lecture later where we consider the case of free fall. It turns out that objects falling near the surface of the Earth, and falling actually could mean going up or going down, those objects are obeying constant acceleration downward due to gravity. We'll come to that next time. So we'll first talk about how these things are related in their graphs. Then I'll derive the equations that we'll be using to solve problems like this. To show you where they come from, these equations will be on your equation sheet. And then we'll do 3 examples. So the classic 2 trains meeting, reaction time of a driver, and then how long we need to make a highway on-ramp. First, the graphs. So we're talking about one-dimensional kinematics, which means that we're talking about an object that travels in a straight line. Now, in fact, we talked last time that it could just be the projection of the object's travel in the straight line, but for now let's think about it as an object traveling a straight line. So maybe we have a car, and that car is moving. Looks more like a limousine here. And that car is moving along the x-axis. Maybe at this moment in time, it has some velocity that points in the positive x direction. It's sitting there with some position, and we could give these all times. And perhaps it's changing its velocity. So perhaps at this particular moment in time, it's about to encounter a red light, and therefore it needs to stop, and so it's going to have an acceleration that points in the opposite direction. What we'll do is we'll consider the x position, the vx component of the velocity, so we'll look at v sub x as a function of time, and a sub x as a function of time. So let's take each case separately. So constant velocity, and what we'll do is we'll just take literally the phrase that we're given, constant velocity, plug it into these 3 graphs, and then see if we can come up with the other 2 graphs, knowing what the connection is between them. So for constant velocity, it just means that the velocity is constant. So we'll plug that in. Let's say that the velocity is positive. So for all time, the velocity sits on that line there. Okay, well, let's go to acceleration first, because that's sort of the simpler way to do it. Remember that in going from a velocity to an acceleration graph, we use the fact that the acceleration, or the average acceleration, is the change in the velocity over the change in time, meaning it's the slope of the velocity versus time graph. And for instantaneous, we look at this change in velocity at a particular moment on the graph, meaning we look at the tangent line. But in this case, it's very simple. So any point on the graph that you look has exactly the same slope, and that slope is 0, so we just draw that on the acceleration graph. So in this case, acceleration in the x direction at all times is equal to 0. Okay, Now, what about the x-graph? Well, we have to use the logic backwards. The logic, remember, is the same as the previous one that we talked about. It is that the average velocity in the x direction is delta x over delta t, meaning it's the slope of the x versus t graph. So we know what the slope of the x versus t graph is. We know that it's some positive number and it does not change. So the x versus t is a graph of positive slope that does not change. And so we can draw that. So there's a possibility. I say a possibility because we could have chosen a different graph. So if we know the number here, maybe this is 12 meters per second, then we know exactly the slope. So this is one possible line with a slope of 12. But we could have drawn a different one. It could have been any one that is parallel to that one. So it could have been this one, it could have been this one, it could have been this one. But it would look like one of those there. So these are the graphs for constant velocity motion. Now let's look at constant acceleration. We need to start with the literal statement, which is that the acceleration is constant. Why don't we try the case that's drawn up here, where the acceleration is pointing backwards on an x-axis that points to the right. So if you were to find the component of this vector, the ax value, I guess we can do it. So let's take the a vector and place it on the coordinate system. Then the component, the x component, would be this number, a sub x, but that is less than 0. So I chose it for this example to say, well, my car is decelerating. My car is going back, is slowing down. And it turns out that if that's the case, then the acceleration is the opposite direction of the velocity vector. And if my position axis goes forward and the acceleration goes backwards, then ax will be negative. So let's see what happens if we do that. So we choose our acceleration to be some negative value, everywhere negative. Well, we already figured out how to do this when we looked at the velocity versus time graph last time. If we have a constant value for the acceleration, then that means a constant slope on the previous graph, the velocity. So maybe we'll draw a line with constant slope. The difference is that now the slope must be negative. So let's draw this slope here. So this could be the graph of a car approaching a stoplight. So it has some positive velocity, a velocity vector that points in the positive x direction. And as time goes forward, the velocity gets smaller and smaller until it comes to 0. And that's the moment that the object, the car, stops at the stoplight. Okay, now what is the position? Well, now we see that the velocity is decreasing all the time, which means that the slope of the x versus time graph should be decreasing all of the time. So the slope is decreasing. However, what's the value of the slope? Well, at every moment in time on this graph, the slope, the v, is positive, so that means the slope up here must be positive. So we need to have a graph which has a slope that is positive, but a slope that is getting closer and closer to 0. And in fact, the slope gets to 0 at this moment here, at that moment in time. So let's draw that first. So we know the slope has to be 0 there. Then we can draw a graph that has some positive slope at the beginning, some smaller positive slope later, smaller slope until it gets to 0. So this could be the graph of a car which is heading towards the stoplight at this position here. So it's getting to that position, but it's getting there slower and slower. And then of course, if this continues to be flat, then that means the position is constant over time, meaning the car is staying at the stoplight. So these are the ways, you should understand what these graphs look like so that you can recognize or you can reproduce the graph of a motion for constant velocity or constant acceleration. Now let's derive the algebraic equations that we can use to solve problems. And I should tell you what we're after here. We're going to look at equations that are position versus time, velocity versus time, and acceleration versus time. And what we mean by that is the position at a given time in terms of the position, the velocity, and the acceleration at some earlier time, which we'll call the initial time. And in fact, we'll call that time t0. So our time interval that we're going to look at is going to be from time is equal to 0 to time is equal to t. So this is like our initial time, and this is our final time there. And we'll see how that comes about in just a minute. So when we do that, we'll be able to answer questions like, well, here we're going to do the constant velocity motion. So something like, what is the x position of a car that started at 5 meters on the x-axis and drove at constant velocity for 10 seconds. I guess we need to say Vx equal 5 meters per second, something like that. So we'll be able to figure out the position, knowing where it started, initial position, how long it went, and what the velocity is. That's what our equations should give us. Okay, so what are the equations for constant velocity? We already saw them graphically. That's what we did in the previous section. Well, one of them is extremely easy in the same way that one of those graphs was extremely easy, and that is the velocity versus time function. Since we're talking about constant velocity, the velocity at every time is going to be equal to the velocity at time 0. And we're going to give that a special name, which is v0 sub x, meaning it is the initial velocity at time is equal to 0, x component. So if something's moving on a straight line that we call the x-axis, then it's just the component of the vector that might be positive or negative. We'll generalize later to objects that move in two-dimensional space, and we just look at the projection of them along the x-axis. So that's one equation. Now we want to find the position. So how do we do that? Well, to do that, we use one of our definitions from kinematics, which is that the average velocity in the x direction is equal to delta x over delta t. Now let's use the time interval that we were talking about, which is x at time t is our final minus x at time t0 is our initial. And we chose to make t final just t and t initial 0. And now we know, since we're talking about constant velocity, the average velocity at any moment is going to be equal to the constant velocity, which is the initial velocity. So I can replace this with v0 sub x. So what does that lead to? Well, I'm looking for a function of position versus time, so let's write it as x of t is equal to x of 0 plus v0x times t. And I could also write that as giving x0 a special name. X of t is equal to x naught plus v0x t, or v naught x. And that's our second equation. That's position versus time. Finally, what's the acceleration? Well, that's also easy because the average acceleration in the x direction is equal to delta vx over delta t. And delta vx is vx at time t minus vx at time 0 for the time interval that we're choosing. But we already know that this is equal to v0x. That was our equation for velocity. So those two things in the numerator are the same. The acceleration is not changing over any time interval, and therefore we can write that a 0x is equal to 0. So the acceleration does not change. I guess I shouldn't say that. I should say ax at any time is equal to 0. So in summary, we have, let's write them as position, velocity, time. We have x of t is equal to x at time 0 plus v at time 0 in the x direction times time. We have the velocity in the x direction at any time is equal to a constant, v0x, and the acceleration at any time is equal to 0. Sometimes we'll just leave off that equation altogether. These are the equations for constant velocity. Now let's look at the equations for constant acceleration. So again, one is easy. Constant acceleration means simply that the acceleration a sub x at any time is equal to the acceleration at the initial time. Constant acceleration. So again, we'll give it a special name. Ax of t is equal to a0 sub x, the initial acceleration. To find the velocity, we'll use a similar method as finding position from velocity in the previous one, and that is that the average acceleration is equal to delta vx delta t, which over our time interval is vx at the time final, t, minus vx at the time initial, 0, divided by t minus 0. So what is that? Well, I can multiply both sides by t, and I get vx at time t is equal to, and let's give this its name, this is v0 sub x. So that's going to be v0x, the initial velocity, plus ax times time. I guess I should say we already know that ax is constant, so this is going to be a0x times time. So it's whatever the chosen acceleration is, we can write that as the initial acceleration because it's the same at all times. That's our second equation. And this one is just a little bit more difficult because we need to come up with some other piece of information to use. And we'll do it by looking at the velocity versus time graph. So if you have a constant acceleration, so let's assume here that we have a positive acceleration, some positive number, then the velocity versus time graph is a positive slope linear line. This would work for a negative slope as well. It's just easier for me to draw it like this. And over any time interval, so for instance the time interval from time 0 to some time t, the average velocity is, well, on any graph, it's the average of the velocity over all times. That's what we mean by the average velocity. But in the particular case of a straight line, you can also find the average velocity by looking at its initial and final values. It's actually the average value of v initial and v final. So this is the velocity at time initial, and this is the velocity at time final. So just to write that in an equation, v average x is equal to vx at time t plus v0x divided by 2, the average of those two numbers. And that's useful because we have an alternative expression for v average, which comes from kinematics. This is a different one, which is only true when the line is a straight line. It wouldn't be true if the line was curving, meaning if the acceleration was changing over time. So what do we get from that? Well, let's see. So if we want to express that using the other equation, then we can say, well, we have v average x is equal to vx of t plus v0x all over 2. But v average x is also equal to delta x over delta t. So that's x of t minus x of 0 over t minus 0. Now we can write this as x of t is equal to multiplying both sides by t and then adding x0. So remember, x of 0 becomes x sub 0. Then this becomes x0 plus vx of t over 2 times t plus v0x times t over 2. And now we're not quite finished. We have to plug in our previous expression for vx of t. So what does that become? Well, it becomes x of t is equal to x0 plus 1/2 times vx of t, which was v0x plus a0xt, like that, multiplied by time. And I think I screwed it up, didn't I? Did I screw it up? Let me see. Well, let's just go through the whole thing. And then we have plus, oh no, I didn't screw it up. v0x t over 2, that's our last term. So that becomes x of t is equal to x0 plus, and what do we have? We have a 1/2 v0x times t, and we have a 1/2 v0x times t, and that just becomes v0x times t. And then we have a 1/2 a0x times t, and that becomes 1/2 a0x t squared. There's our equation. Okay, so for constant acceleration, we've come up with these three equations, this, this, and this. We can summarize them. So again, let's write them starting with position. So x at time t is equal to x0 plus v0x times t plus 1/2 a0x t squared. The velocity in the x direction is v0x plus a0x times t, and the acceleration at any time is a constant. That's what we mean by constant acceleration. Interestingly, these equations now are the algebraic form of those graphs that we made in the first section. So we started out by drawing a constant line for the acceleration graph. Remember, we drew a negative constant. That implied a straight line. So you notice that this is a straight line relationship. It's like y is equal to mx plus b here. And then that implied this changing slope graph, which we now see is a quadratic or a parabola. So x is a parabola in time. This is our set of constant acceleration equations. Okay. It turns out that it's useful to find a fourth equation. So this is all of the information that you can find about constant acceleration motion. But there's a useful quantity that we can get, which is an equation that relates position and velocity without having to talk about time at all. In algebra, what we'll be doing is we'll be solving these two equations and eliminating time to create one equation. So let's try and do that. So this is just a little bit of algebra trickery, and I'll just try and do it quickly. So if we label these as equation 1 and equation 2 and equation 3, then let's take equation 1 first, and we'll rewrite it. So equation 1 is going to be x minus x0. So I subtracted x0 from both sides. And I'm going to multiply it by something, so I'm going to give myself some space. And that's going to be equal to v0x times t plus 1/2 a0x times t squared. But now I'm going to multiply through by 2 a0x. And we'll see why we do that in a moment. So that becomes 2 a0x times that. And this becomes, well, just a0x squared. The 2 cancels the half, and the a0 becomes squared. So this equation is the same as equation 1. I've just rearranged it and then multiplied by 2a0. Okay, now let's look at the second equation. So the second equation, I can write that as vx at time t minus v0x, and that's going to be equal to a0x times t, and then I can square that. So that's actually equal to, well, let's write it on the next line. If I square that whole thing out, I get vx squared minus 2 vx v0x plus v0x squared, and that's equal to a0x squared t squared. Okay. Now at this point, I can replace this vx with this equation up here. So let's do that. So I have vx squared minus 2v0x times v0x plus a0x t plus v0x squared, and that's equal to a0x squared t squared. And now let's see what we have. Well, I have 2 v0x squared with a minus sign, and I have v0x squared here. So that will become minus v0x. So I get vx squared minus v0x squared. I said v0x, I meant v0x squared. So 2 v0x squared with a minus sign plus 1 positive gives me 1 negative. And then I also have minus 2 v0x a0x t, and I think I lost something here. I should have a t squared there, shouldn't I? Oh no, I don't. So what do I get? So I can move that to the other side. I have a0x squared t squared plus 2 v0x squared t. No, wrong. I have, sorry, I was looking at the wrong term. It's this term here. So I have 2 v0x a0x t here. But this whole thing is just equal to this whole thing up here. So that means I can write vx squared minus v0x squared is equal to 2 a0x x minus x0. So that is sort of a fourth equation. It doesn't contain any more information than the three equations we already found, but if you notice, that equation allows us to compare the velocity of an object to its position while under constant acceleration, whereas in these equations we have to consider the time in order to compare velocity with position. And you could do that. So we'll see in problems that there are sort of two ways you could do them. This offers us sort of a shortcut, and we'll use it once today. Okay, let's do an example. And for this first example, I'll try to sketch out sort of the method that one uses for a problem like this. Most of this so-called method is just how one should do sort of a physics problem, meaning draw a picture, give yourself names for quantities, variable names that you can use in equations, choose a coordinate system that's convenient. So much of this will pass forward, not just for this kind of problem, but for other problems as well. So let's look at the problem. So we're told that we have a train leaving Chicago for Detroit, so heading east. That's going to be a 300-mile trip, and it's traveling at 60 miles per hour. And at the same moment, a second train leaves Detroit, heading west for Chicago, and it's traveling at 50 miles per hour. So where do the trains meet and when, as compared, of course, to the moment that they left? Okay, so let's draw it out. So I guess we should put Chicago and Detroit on our picture. We have two trains, so I don't know how to draw a train, but maybe something like this. And we have another train that's headed in the opposite direction. We know the distance from Chicago to Detroit, so let's give that a name. We'll just call it D. So we say D is equal to 300 miles. What else were we given? Well, we were given the speed of each train, so let's make those speeds into velocity vectors. So we have a velocity vector of, let's call it the Chicago train that is pointing to the right. So that's the Chicago train. And VC was given to us as 60 miles per hour. So remember, when I write VC without an arrow over it, I mean the magnitude of this vector is equal to this number. And the other velocity vector should be a little bit shorter, I guess. And that's the Detroit train, the train coming from Detroit. And it's going at 50 miles per hour. Is that all that we have? That looks like about all that we were given. Now, the next step is to try and put a coordinate system to this. So it's going to be useful to talk about this in terms of coordinates. And remember, we said we're talking mostly about motion along a line, and we might as well call that line the x-axis. So you could put that line however you like and put the origin however you like, but I think it's easiest if we put maybe the origin in Chicago and then let the line go out to Detroit. So this is going to be our x-axis. That would be our y-axis, but we're not going to deal with any of that. So you can see a couple of things now. You can see, for example, the initial position. Oh, I guess I should talk about times too before I say initial. Well, I don't really have a good way of saying it because this moment in time is not the initial time. It's after they already left. But the initial moment in time would be when this train is back here at an initial position of 0, and when this train is back here at an initial position of whatever this number is, well, it's going to be D. So the initial value of train Detroit is going to be at position 300 miles on that coordinate system that we chose. The other thing that you can see from choosing a coordinate system is that we now can find components of these vectors. If you place this vector on such a coordinate system, you'll get a positive component, and if you place this one on a coordinate system, you'll get a negative, and you'll see that we'll use that. So that's picking a convenient coordinate system. Now we want to try and see what type of motion we have and then pick out equations from the ones that we derived. So it's helpful to have your equation sheet in front of you to see what those equations are. And it's also important, of course, to look at the question to see what we're trying to figure out. So what we're asked is, where do they meet and when? So what does it mean to meet? Well, it means that these two trains will, hopefully they won't hit each other, hopefully they're on parallel tracks, but there's going to be some point here, which we could call x meet, where they are at the same position. That's what it means for them to meet. So what we mean is that at some moment in time, we'll have x of the Chicago train equal to x of the Detroit train. And we could call that position x meet, whatever it is. So that's an unknown right now. We don't know what that is. But look at this. Just by trying to write out what we were told, we arrive at an equation. And that's going to be useful to us. So we're told that we need to find x Chicago equal to x Detroit. Now we use what we have already found, which is that these things are going with constant acceleration. So motion with constant, sorry, not at constant acceleration, constant velocity. So these two trains are both moving with constant velocity. So I can use the position equation for motion with constant velocity. Let's go back and look at it. Back here, it's going to be this equation here. X at time t is equal to x naught plus v0 x times t. So when we write the equation, I think I have this listed as 4a, write out the entire basic equation first, basically as it appears on your equation sheet. So for motion with constant velocity, we have x at time t is equal to x0, and that's x0 Chicago, plus v0 Chicago x times t. Detroit is going to be x0 Detroit plus v0 Detroit times t. And those times are the same, but nothing else in this equation is the same between the two trains. So that's writing out the equation as it sits on your equation sheet. Now I'm going to use the names that I gave up here to try and plug them in. So let's do that. So just one by one. So what is the initial position of the Chicago train? Well, based on the coordinate system I chose, it's right here at the origin. So I can write x0 Chicago is 0. What is the initial velocity of the Chicago train? Well, this is constant velocity. What is the velocity altogether? Well, it's going to be the vc value, but we need to check whether the component is positive or negative, because this has a component. It's the x component of this velocity vector. So we look at it and we say, oh, if I place this vector on a coordinate system like that, it's going to give me a positive component. So I can write this as plus v Chicago, the speed of the train, times t. Now we go to the right-hand side of the equation. What is the initial position of the Detroit train? Well, the initial position of the Detroit train was in Detroit, right here, and we said it's this position on the x-axis, but because this length is d, this number, this tick mark, is also d. So I can write that as d. And the initial velocity of the Detroit train in the x direction, I find by taking the Detroit velocity vector and placing it on a similar xy coordinate system that I chose. Oops. Oh, shoot. I have to pull that forward. So this is my v Detroit. I place it on this coordinate system. And on this coordinate system, this tick mark, this is v Detroit x. And you see that that number is a negative number. It's on the negative x-axis. So I don't plug in v Detroit at this point, but I plug in minus v Detroit. So you can see what I'm doing. I'm writing the components in terms of positive things, in terms of these positive quantities that I defined, in particular the magnitude of the vector. And then I have t here as well. Okay, so what does that mean? Well, at this point, let's take a look at our equation. We were given the two speeds, we were given the distance, and t is the only unknown. So that means I have one equation, one unknown. It means I can actually solve this problem. And the rest of it is just algebra. So let's do that. Let's move the vdt to the other side, so add it to both sides. So we get vct plus vdt is equal to d. We can pull it out, the t. What's that called? The opposite of distributing? Factor out. Is that what it's called? And then I can solve for t. There. So this is the solve for with algebra step. What was the step that I missed? Express the components in terms of positive variable names chosen above. So we did that here. For instance, the x component of the Detroit train's velocity was negative, but the x component of the Chicago train's velocity was positive. And now only that I've gotten to an equation that says the thing that I want is equal to a bunch of stuff, do I actually plug in numbers. And that is 300 miles over, and VC was 60 and VD was 50. So what does that give us? Let's just look at the answer here. That is 2.7 hours, approximately. Okay, so we found the first answer, which is, not the first answer. We found when they met. When we used the position, we immediately lost the actual position, x meet. So what does that mean? Well, it just means we need to go back to this equation here. So maybe let's write the Chicago trains. So to find position of meeting, x meet, well, x meet, remember, was equal to x Chicago of time t. So what is x Chicago of time t? We already used that equation. It is x Chicago initial plus v0 x Chicago. I guess I should write it as v Chicago 0x maybe, times t. So what is that? Well, we know that x Chicago initial was 0, and v0 Chicago is 60. And now we have the time. So we can find the meeting place with respect to Chicago, and it turns out that that's about 162 miles. So where are they going to meet? Well, halfway in between would be 150 miles, and they will meet a little bit further than halfway in between, somewhere about 160 miles. You might then, at the very end, go back and say, well, does that make sense? And it does, if you think about it. If the Chicago train is moving faster than the Detroit train, then in the same amount of time, Chicago will have gone further. So it goes a little bit further past the midpoint, and we found exactly the point at which they met. There's another approach that we can take here that's useful either to check ourselves or sometimes to do the entire analysis, and that's to take a look at the position and the velocity versus time graphs. So let's look at the position versus time graph. So this is not the same as the coordinate system I drew above, because my horizontal axis is time and my vertical axis is x. So we had this x, we had the trains here with their velocities, and now we're taking this entire x-axis and we're moving it to a vertical axis. Okay, so this position here, x is equal to 0, that's Chicago, and this position here, that's going to be Detroit. So this is Chicago and Detroit, where this is 300 miles on the x-axis. That's this number. So let's carry that forward. So now let's draw a graph for each of the motions. And we already know from the very first section of this lecture what the graph should look like. We know that if you have constant velocity motion, that you have a linear graph. And we also know that both of those linear graphs will start at the same place. And we know that the Chicago one has a positive v sub x, right? We said that the Chicago one has a positive v sub x, and that goes back to the fact that its velocity vector points in the positive x direction, whereas the Detroit train has a negative v sub x because its velocity vector is pointing backwards. So putting all of that together, one more thing is that Chicago has a bigger slope than Detroit because it has a faster velocity. There's the Chicago one, and now I don't want to draw one that has exactly the same slope, so instead I'll draw one that has a smaller slope. So where do they end up? Well, there's some point at which they meet, and you can see that that point is more than halfway from Chicago to Detroit, and that appeared because this slope in absolute value is smaller than this slope. And we could in fact find that here. We know what those slopes are because we know that we know the values of the velocities. So we could do a little bit of triangle trigonometry here, and we could actually figure out what the value of t is and what the value of x meet is. And even if we don't do that, it's useful to sort of make this graph to sort of see what's happening. Sometimes it's useful to do that at the very beginning. Okay, let's try another example. The reaction time of the average driver is a little bit less than a second, 7/10 of a second. If a car can slow down with an acceleration of 12 feet per second, then compute the total distance covered in coming to a stop after some signal is observed. So the idea is to figure out how long it takes, or not how long, but how far it takes to stop, given two different initial speeds. So if you're being very cautious and you're driving 15 miles per hour, what is the distance, the stopping distance? And if you're being, if you're driving on a highway and you have to stop, then what is the stopping distance? Let's see how those compare. This stuff was given to us in units that are not SI, they're not standard units. So I just converted everything to SI units. Remember, SI is meters, kilograms, seconds, MKS. So it turns out that 12 feet per second squared, that's the acceleration, and that's about 3.5 meters per second squared. 15 miles per hour is 6 or 7 meters per second, and 60 miles per hour is 27. I say this is a nice thing to remember because we're going to be using meters per second all the time in this class, and yet in your life you use miles per hour. You're much more familiar with that. So it's almost a factor of 2. You basically divide miles per hour by 2, maybe a little bit more, and that's how you get meters per second. So it's nice to have some sense about what that is. Okay, so let's try and solve the problem using the method that we had before. Well, remember, the first step is to try and draw something. So we try and picture it. What is happening here? Well, we have a car. And it starts out at some moment here. And what is it doing? Well, it's driving with some constant velocity. So we could draw some constant velocity, and we might call that the initial speed there. And that value is going to be either 15 or 60, or I guess I should say 6.7 or 27. But let's not plug it in, because it turns out we can do this problem, we can do both of them at the same time and then just plug in these two possibilities at the very end. So there's some initial speed, and it's going to drive with a constant velocity there. And at this moment, I guess it sees something on the road that alerts the driver to stop, to put on the brake. But of course, the driver can't do that immediately. There's some amount of time that goes by before the driver is able to put on the brake. And only once the driver gets to this position, so this is some 0.7 seconds later, does the situation change, where the driver is still going forward, I guess with a smaller velocity, but now there's going to be an acceleration which is pointing backwards, because now they're going to start to slow down. And then at some later time and later distance, we're going to have the car come to a stop. So let's just draw that. So this is where v is equal to 0 at this moment in time. So we've labeled some things. The acceleration is the same for both cases, so we can write that in. It's 3.7 meters per second squared. And you notice I pointed it backwards because it's slowing down. If you point an acceleration opposite to a velocity, that means slowing down. What else can we do? Well, we might include time here. So this is time is equal to 0, and this is time is equal to t reaction, which is equal to 0.7 seconds. And then finally, this is t stop, and we don't actually know what that is. We don't know how much time it takes. Maybe we'll need it, maybe we won't. Let's also give ourselves a coordinate system. So I can draw here that the motion is all on the x-axis, and we might as well put the origin back here at time t0. I can't see any reason why not. And then we can give ourselves some position values or some distances. So this is the amount of distance traveled during the reaction time, so we could call that d-react. And again, I don't know what that is. And then this is the rest of the stopping distance. So I don't want to call it d-stop because that should be the entire thing. So I guess I'll just call it d-slow. And again, I don't know what that is. And then we'll say the stopping distance is equal to d-react plus d-slow. And that's what we're after. We want to know what the total stopping distance is. Okay, is there anything else we can do here? I'm not sure. I don't see anything. So let's try and proceed. So what are we trying to figure out? Well, we want to know what the total distance covered is after coming to a stop, after the signal is observed. So what is that? Well, this equation here actually seems to be a pretty good one. The total distance stopped is the reaction distance plus the slowing distance, and we could use that. So let's try it out. So I guess we should say the distance stop is equal to the distance react plus the distance slowing. And now let's try and use our kinematics to figure out what that is. Well, the distance of the reaction is going to be the distance that it takes while you're moving with a constant velocity. So that's going to be like the x minus x0 of constant velocity. So let's write down our equation. We have x of t is equal to x0 plus v0x of t. So I can write that as well, I guess let's take it a little bit slower. Let's call that the delta x of the reaction. So I can write this as x of t minus x0 is equal to v0x times t, and that I could call the delta x. The d slow is going to be the delta x for the slowing. And that one will come from a different equation because this here is constant velocity. For the second phase, we're going to have to use constant acceleration. So that's going to be x of t is equal to x0 plus v0 xt plus 1/2 ax t squared. Okay. Yes. And so now let's use those. So taking these two things together, we can get delta x. And so delta x reaction during the constant velocity is just going to be v0x times the amount of time. So this is going to be the reaction time. There, I'm using this piece right here. And the slowing distance is going to be, well, it's going to be v0x at the initial, but our initial is slightly different here. It's going to be the initial at this moment here. I guess that's not different because it's moving with a constant velocity. So all the way through, it's going to have v0x. And then the amount of time that it takes from here to here is not the total time from here to here, but it's going to be t stop minus t react. So our time now is t stop minus t react. And then we have plus 1/2 times the acceleration, ax, times the same interval of time, t stop minus t react, but squared. So I've used this equation here for the second delta x, and I've used this equation here for the first delta x. Now let's try and put some of our variable names in there. So what is v0x? Well, that is a positive component of the v0 vector. We see it's pointing forward. So we can just write that as v0. We still have t reaction. v0x at this moment is again the same because it keeps the same velocity up until that moment. So that is just v0. We have an unknown, t stop, and we have the known, t react here. And then we have plus 1/2 and ax. Well, now we look at ax at the a vector and we see that it points backwards, so that's going to be a negative component. So I'm going to write ax as minus a, minus the magnitude. So that's minus a, and then I have t stop minus tr squared. So the distance to stop is written like that. Okay, so that's something that we can do. Now what do we do with that? Well, it looks like we're going to need more information. So why do we need more information? Well, this is one unknown, but this is another unknown here. So it looks like we're going to have to do some more work. I guess I need a new page. So what can we do? Well, maybe we can try out a different equation. So the way that you do these problems if you don't know what you're doing is you try and write down something that's true, check to see whether you can solve it with algebra, and if you can, if you get one equation with one unknown, then you're done. If you can't, if you get one equation with two unknowns, then you need to come up with another equation, and if you have two equations, two unknowns, then usually you can solve the problem. So why don't we try to use that fourth equation that we had to look at only the second phase here. So let's try that. So let's write down that equation. That equation was v0, it was vx of t squared minus v0x squared is equal to 2ax x minus x0. Okay, so let's see what we have here. So we have vx at time t. So what do we mean by that? Well, now I'm talking about the interval of time from the moment that you put on the brakes here to the moment that you stop here. So the final value of v is just going to be 0. So I can plug that in. The initial value of v at that time interval is the thing that we were calling v0. So it was the given 15 miles per hour or 60 miles per hour. Ax, that's going to be the x component of this vector. So that's going to be negative. So that's going to be minus a. And then x minus x0, well, that's the difference in position from here to here. So that's what I called d slow. So what do I get out of this equation? Well, I get minus v0 squared is equal to minus 2a d slow, which I could write as v0 squared is equal to 2a d slow. Let's put a box around that because we know it's a true equation. Now, are we able to finish the problem? Meaning, do we have two equations with two unknowns? Well, this one I have d slow as an unknown, and here I have two other unknowns, d stop and t stop. So it looks like I can't quite figure it out from there. However, this equation I can solve directly for d slow. So what's d slow? That's going to be v0 squared over 2a. And so v0 squared over 2a, we can solve for that because we know exactly v0 and a. We'll come back to that in a moment. If I can find out what dr is, then I can solve the whole problem. But dr was just this quantity here, and we know both of those things. So it looks like we have dr is going to be equal to v0 times tr. Let me write that out completely. Starting from the main equation, we have x of t is equal to x0 plus v0 xt, and we're applying that from this t is equal to 0 to t react. That's going to be the dr distance. And we were given t react, so we get x of t is going to be dr, x0 is 0, v0x is the x component of the initial velocity, that's positive v0, and t is equal to t react. So we just get to this equation here. So these two equations actually have solved the problem for us. So d stop is equal to d react plus d slow, and that is v0 tr plus v0 squared over 2a d stop. Let's go back to what we did first quickly. So I tried it using the equations with time, and this is certainly true, but it didn't get me to the answer. Now, what I could do, now that I'm going to be able to get some more information, I'm going to be able to find out what d-stop is I could come back and I could solve for t-stop. So this is a quadratic equation in t-stop, and I could figure out how much time it takes to stop. That could be useful, but it turns out that that wasn't asked, so I don't need to do that. We were only asked about the stopping distance. So this will happen when you're solving problems like this, is you write something down, you make sure that everything you're doing is correct, and you end up with a true equation, but it might not be useful. I guess the most important thing is not to panic and to just move on and try something else. So I tried a couple other things, and I was able to get to the answer. So let's find out what that answer is. Well, in the case of the school zone, so if you're going 15 miles per hour, then we have V0 was 6.7 meters per second. So we have 6.7 meters per second. T-react was 0.7 seconds. V0 is 6.7 meters per second. We square that and we divide by 2 times the acceleration, which was 3.7 meters per second squared. So let's find out what that number is. Plug it into my calculator. 6.7 times 0.7 plus 6.7 squared divided by 2 divided by 3.7. So I get 10.8 meters approximately. Okay? Now what if you're going 60 miles per hour? So what do you think? Take a guess. Well, this is going to be, the initial velocity is now, I think, 4 times larger, right? So it's going to be 27 meters per second. Then you have the reaction time, plus 27 meters per second, and we square that whole thing, divided by 2, and the acceleration is the same car. It's able to do an acceleration of a certain amount. So we get 27 times 0.7 plus 27 squared divided by 2 divided by 3.7, and we get 117 meters approximately. So notice you increase the speed by a factor of 4, and the stopping distance doesn't increase by a factor of 4. It increased by a factor of about 10 there. So that's interesting. We didn't know that before. Okay, one last question. The typical acceleration of a car is 1 meter per second. Considering that, considering that a car must go from 0 to 60 when getting on the highway, how long should the on-ramp be? So let's just draw our picture. So here's our car. At this point it has a velocity of 0, and we want it, once it gets onto the highway, to have a velocity of, so V final, of 60 miles per hour. And we want to know, what is this distance? We don't know what that is. Let's give ourselves a coordinate system. Again, we'll put the origin at the starting point. So this is the xy coordinate system. This is the x final position, and that's going to be equal to d. And v final is 60. We don't have anything about time again, so it might be useful to use that special equation that doesn't involve time. So let's try it out. So let's write it down. V0, it's not V0, I always write it wrong. It's Vx at time t squared minus V0x squared is equal to 2ax x minus x0. I left out one thing here, which is the acceleration vector. And if you're going to be moving, if you're going to be speeding up, then your acceleration should point in the direction of motion. So we have an acceleration vector, and we were told that the magnitude of that is 1 meter per second squared there. Okay, so it might be a good idea to state how you're going to use it. So we'll say from t is equal to 0 to, to x final, to when it gets on the highway. So from this point here to this point here. So my final velocity then will be the value that I drew over here. It's going to be v final. So that will be v final squared. Notice that the v final vector has a positive x component, although because we're squaring it, it doesn't matter. The square would always be positive. v0x, well, we go back and look at the initial moment in time, and we see that our v0 is 0. So we don't have to write it as v0, we can just write it as 0. Then we have 2 times ax. Well, we look back at our a vector. We say that vector points in the positive x direction, so its component ax is just a. And finally, we have x final minus x initial. Well, x final is d, and x initial, back here, because of my chosen coordinate system, is 0. So we see that v final squared is equal to 2ad. Well, we were only asked for d, so now we can solve. So it's v final squared over 2a. And if we want to get to 60 miles per hour, remember that was about half was in meters per second. So let's just call it 30 meters per second. Square that. And then we have 2 times the acceleration, which is 1 meters per second squared. So what do we get? Well, that's going to be, I guess, 900 divided by 2. And when you cancel out all those units, it should come out to be meters. So that's 450 meters. That's quite a distance, half a kilometer, that you need in order for a car to get up to speed, in order to get on the highway. And if you look at one of these highway on-ramps, you'll see it is about that distance. And that concludes this lecture.